Okay, so we've just said that the pigeonhole principle says that if you have n holes and more than n things, then some hole will have at least two things. And that's very easy to prove because if each hole has just one thing, then you can have at most n things. So now we can see if we can sort of make this stronger. So like suppose you have four holes and you have say nine things. Then you can show that in some hole you need to have three things. Because if not, you have at most two things in each hole and that will add up to eight. So like how can you generalize this? So the generalized form says that if you have k holes and n pigeons or things, then some hole will have at least the ceiling function of n by k. And so intuitively also you can try to think of it like if you're spreading things out as evenly as possible and you're putting n by k things, then you'll have approximately n by k things in each hole, right? So that's a very intuitive way of looking at it. But we'll also formally prove this. So there are two cases. One case is when n is divisible by k. So in that case, if n is equal to mk, but you have less than k things in each hole, then in total you'll have k times, at most, okay, you have k holes, so you have at most m minus 1 things in each hole. And that will add up to m minus 1 times k, which is obviously less than m. And in the other case, if n is more than k, then you'll have n is equal to say mk plus r. And this quantity will be m plus 1. Right? In this case, the quantity was m. And here, if you have at most m things in each hole, then you'll have only mk things in total, which is less than m. So in both cases, you need to have at least ceiling function of n by k things in each hole. And even though the proof is sort of algebraic, I just try to think of it in a intuitive way of spreading things out as much as possible and then seeing which hole, like what the maximum value is in some hole. And that might be a more useful way of thinking of it sometimes. So we'll start with very basic problems just to get a hang of this. So the first problem is this: show that in a party there are always two people who have shaken hands with the same number of people. So basically you have n people, everyone shakes hands with some number of people, and you want to show that there are always some two people who have shaken the same number of hands. So you can try this. And feel free to speak up if you have any ideas.
So we assume for the first problem, we can assume that we have n people, and all of them, for the sake of contradiction, we can assume that all of them uh, have shaken hands with different number of people. Like P1 has shaken hands with some k people, then no one else would have done that, and then that thing will become holes, and we'll see that the two persons will have lie in the same hole, that is they shake hands with the same.
Okay, so you're saying we assume that everyone shakes hands with a different number of people, right? So if there
Yeah.
are n people, then there are how many possibilities? Either you have 0, 1, and so on till n minus 1. There are n minus 1 possibilities of the number of hands you've shaken. We need to somehow reduce this to n minus 1 because now you have n possibilities. So how can you do that?
The both the cases when 0 and n minus 1, these are not possible, since there is one person who has shaken hand with all of them, and that's why there cannot be a person who has shaken hand with
Yeah,
none of.
exactly. So both of these together can't be that. So that means there is at most n-1 holes, like number of people with whom you shook hands, and you have n people. So there must be some hole with 2 people. So like some 2 people have shaken hands with the same number of people. I hope that is clear. That's like very simple. Okay, now we can try this problem. So you're given 5 points on the plane, and they all have integer coordinates. So, and you're taking all of their midpoints, and you have to show that some midpoint also has integer coordinates.
I have done this one. Like I previously did this.
Okay, I can send you a different problem. I got disconnected for a second. Did someone say something? If so, can you say it again?
I send my solve through private chat.
Yeah, we can also like say it now. It's correct. Okay, so the idea is you look at the possible parities you can have of the points. So the possible parities are odd, even odd, odd, and even, right? These are the only possibilities. So now if you have 5 points, some 2 points will have the same parities for both points. So when you add them, then you'll get 2 even numbers. And when you divide by 2 to take the midpoint, you'll get integers. Because for taking the midpoint, you're just taking this, right? So yeah, that's the idea for this problem. Now we'll do a similar kind of problem, which is given 13 points with integer coordinates, show that the center of gravity of some 3 of them has integer coordinates. So for center of gravity, we're just taking the 3 coordinates and we are taking their averages. So that's what center of gravity is. It's like the centroid.
Again,
So given 13 points on the plane, we need to show that the center of gravity of some 3 have integer coordinates. And center of gravity just means basically this. Like you're taking the centroid of 3 points.
okay.
Okay.
Maybe mod 3 could help. Like there we took mod 2, here mod 3.
Yeah, try something like that.
So we can say that like three numbers of the same parity will be divisible by 3, and we can use that, right?
Yeah, we need the both the sums to be divisible by 3. You know,
I guess here there are 9 possibilities since there are 3 remainders possible. So we get one
Mhm.
extra one which makes like 0, 1, 2 will make it will make the x coordinate integer. But I am not done with the y.
Okay, fine.
You will get 12 possibilities, I guess, when you do modulo
How
3.
how are you getting 12?
Um, let's check. So one, x2, and x3 are 3 numbers. Then
Yeah.
you will get 002, 001, 011, and 211. And if you take the
0, 0.
if you take the
Wait,
combination of
so
these three, you get 12.
okay, but if you're just looking at one coordinate, then in each position you have 3 possibilities, right? So that becomes 9, but you still have to deal with the other coordinate. So maybe there's a nicer way of dealing with the x coordinate that leaves you more possibilities to work with the y coordinate. Can you think of something like that? Like maybe try directly using Pigeon on just the x coordinate.
Like, will there be 4 pigeonholes and 13 pigeons?
Um, yeah, like so there should be 3 hooks, right? Because the x coordinate can have 3 possible values in modulo 3. So basically, you're doing this, which gives you 5 possible things remaining. So now you have 5 points. You know that there must be 5 points, and all of their x coordinates have the same residue modulo 3. So if you add any 3 of them, the x coordinate will be divisible by 3. So now you just want to look at the y coordinates. So can you finish from here? We need to prove this. And to make it clear, what we did over here was we looked at the possible values for the x coordinate. There are 3 possibilities, so 3 holes. Now, by pigeonhole principle, there must be some 5 points such that the x coordinate is the same for all of them. Like they are all in the same hole for the x coordinate. So we don't have to worry about the x coordinate anymore because we know that when we add the 3 of them, we have something 0, 1, 3 because it's the 3 times the same thing as 0, 1, 3.
So here, should we divide it like 5 upon 3?
That won't give us like, because you can have something like 0, 1, 2, 0, 1, right? So that won't guarantee that we have three things with the same parity. But there's something else you can do first. Like in this case, how can you like directly finish? You just want some three things, the sum to be divisible by 3.
There will be at least one and two, no? So there also be
Yeah,
equal to
exactly.
0.
Yeah, so if there are three different values mod 3, then you can have like a 0, 1, 2, and that is fine. If not, then you have like only one sentence. And then you can apply pigeonhole principle. You can have only two possibilities, so that leaves you with some three y coordinates which have all ones or all twos. So in both cases, you're done. Like I hope that's fine with everyone. If someone hasn't understood, please say.
Can you please tell why you divided by 2?
Okay, so you have some five y coordinates, and you want to show that some of those three will be like that sum will be divisible by 3. So if you have some three of them, which are 0, 1, and 2, like all different modulo 3 values, then you can just take 0, 1, and 2, right? Because the sum is 3. So assume it's not the case. Suppose you have only two values modulo 3, and without loss of generality, let them be 1 and 2. That's what we're doing. So in that case, you have only two holes.
Yeah, yeah, okay, got it.
Like we can always guarantee like there will be 1 and 2 present
Hi everyone.
Hello.
Sanjana's there's like raining at her place and it's like bad net. So she's trying to join, so please wait.
Hey, Pranav, yeah, I guess I'm mistakenly given host.
She left, so like it automatically makes someone's host. When she rejoins, she can be host back automatically. Or
Okay.
unless you do any nonsense, it's fine. Or you can make me host back if you want. But also like I'll probably leave because I'm driving. So let's just wait for her to join.
I don't know how to make her host back.
Uh, it's fine. She'll reclaim it herself when she joins. Lavish, can you pause recording until she joins? There's an option to pause and there's an option to stop recording. Click on pause.
Just see the record option.
That shouldn't be happening. Are you on phone?
Okay, so sorry about that. We were having some issues. I'll just enable screen sharing and then start again. Okay, so this is the next problem. I hope the previous one was clear. I think Sai also explained it. So you can try this one now.
In the question, does that mean that there are 17 into 16 males in total forwarded?
17 into 16 divided by 2.
Okay, 17 C2.
Yeah. So one way of thinking about this is you take a person and you consider all his neighbors. And if some two of these neighbors talk to the person about the same topic, then and also they talk to each other about the same topic, then you're done, right? So first maybe try using some pigeonhole argument about a person and his neighbors.
So we can say that she, like that person writes to like 6 people about the same topics, and among those 6 people, like 2 people, like they talk about the same topic. Can you say that?
Yeah, so we basically have a person and he talks to some 6 people about the same topic. So now if any two of these people also talk about that particular topic, then we're done. So now assume that all of these people talk about the other two topics. Now what can you do?
6 upon 3, 2 is equals to 2.
6. No, like now you want to show that there's a triangle among these 6 people, given that they talk about two topics. So how can you do that?
So it's 6 people and 3 topics.
Yes.
So won't we just do 6 by 3?
No, like you want to show that there is a triangle. So how do you do 6 by 3? Like all the edges are connected. Like maybe try the same kind of thing again. Like what we already did. Take a person, look at the neighbors, and do something.
So a person has 5 neighbors
Yes.
and in 3 topics. So 5 over 3 ceiling.
Yes. So he must be talking to some 3 people about the same topic, because now we have only 2 topics among these people. So we're taking 5 over 2 ceiling. So this is 3. So he's talking to some 3 people about the same topic. Again, if any 2 of these talk about that topic itself, then we're done. But if not, then all 3 of them talk about the other topic. So you have a triangle anyway. Does that make sense?
Okay, like first of all we divided by 3 because there were 3 choices, and then we
Yes.
divided by 2 because already one choice was gone, otherwise the triangle would have automatically been made.
Exactly. Like we kept eliminating one topic at a time.
Okay.
Okay. So we'll do one more problem before moving on to infinite PHP. So in this, every point on the plane is colored either red or blue. And you need to prove that there is either an equilateral triangle or a rectangle, both an equilateral triangle and a rectangle with vertices of the same color. So this is not exactly a PHP kind of problem, but since the idea is sort of similar, I wanted to do this as well.
Like there are infinitely many points.
Yeah, like every single point is colored. It's not a grass theory. It's like you're taking a plane and every point has some color. So now we try to use some sort of argument to show that there must be some 3 points forming an equilateral triangle and all 3 of them have the same color.
Shouldn't there be latest points, or is
No,
that
every point, like all the points on the real plane.
okay?
So in the first case, so basically you can pick points and you know that they have a color, right? So try to think of like maybe a grid of equilateral triangles, and you want to show that some 3 points, which are the vertices of a triangle, have the same color. And maybe if you're assuming for sake of contradiction that it's not true, maybe you'll get some specific sort of structure with which you can.
Yes, so I have tried this. First, we take any two red points, and
Okay.
then on the perpendicular bisector of the line joining the 2 points, there must be that line hole must be blue pointed. Like no, but the two equilateral triangles
Yeah.
formed by both sides on the lines must have the blue points,
Yes.
and the distance between those blue points, like similar argument, but the axis is rotated. Now it is just for the blue points having
Yeah.
red points in that line. I've got this much. What can we get out of it?
How did that happen? Like, I didn't understand.
Okay, so we first took some two red points, and the points which form equilateral triangles with them, we know that they must be blue. Like we are assuming for the sake of contradiction that we don't have an equilateral triangle. So then these two must be blue. But now if you look like if you make this into a grid in which all of these are equilateral triangles, then you have this point here. Okay, that won't be that exact, but so like
Okay, I got it.
okay. Okay, yeah, so this will actually be this exact same point. Because if you notice, this distance and this distance are the same as this because all of these are like congruent. So this exact point will have to be blue. Like this exact point cannot be blue, so it has to be red. So can you somehow continue that logic?
Uh, I couldn't get how that distance will be equal.
And like you're taking this grid of equilateral triangles. So like you understand that in that all the triangles will be congruent, right? Like this distance is equal to this distance, and so on.
Oh, okay, okay.
Yeah. So now you can kind of show that everything on this line has to be right, like all the points on this line here, by extending this logic.
Similarly, on the upper line and on the below line, all the points must
Yeah,
be blue.
exactly.
But now, if we draw another line below it, below the blue line, then it must be
Mhm.
red, and that makes the middle line and the below line equilateral triangle, no?
You mean like this?
Yeah,
Okay.
and
So here
sta-
also these are it. Yeah.
yeah. So the point in the below and the point in the middle line, both the red lines, that
Yeah.
makes an equal.
This makes an equilateral triangle. Yeah. So this sort of used a sort of like a similar idea, maybe not directly, but basically what we did was we made a grid to make a lot of things equal, which made us deal with the equilateral condition nicely. For a rectangle, I don't know if a similar argument will work because my argument is kind of different, but you can try this now for a rectangle.
Can we try something like this? Like, first of all, we can eliminate the case when two edges will have blue color and two edges will have red color. When this is the only possible scenario, then we can that case can be uh, easily be cancelled. But the case when we have three a rectangle with three vertices of one color and one vertex of different color, then
Okay.
there are only a limited possible cases. Then I guess PHP could work on that. That
Wait, how
could
are
be.
you eliminating the first case? Like, what do you mean by eliminating?
I'm saying if all the triangles, all the possible triangles could only have two two blue and two red
You mean
vertices.
rectangles, right?
Yeah, rectangles.
Okay.
Then again, if we extend that rectangle to the right side, like we did
Yes. Yeah.
in that, then it will form a triangle.
Yeah.
Rectangle.
Then basically this happens, and yeah. Okay. Fine. So you can ensure that something like this happens.
Yes, but how can you ensure like two blues occur as well? Like you can't ensure that, can you? Like it could
No,
happen
so
like after
he
two. It could be like a blue and red, and a double blue never occurs.
so like in the other case, he is assuming that every rectangle has two red vertices and two blue, like in this form. Like he's assuming this, but then we end up having a rectangle with all four of the same color. Like you just pick any 2 points here, and both of those have to be red if you are doing that assumption. And so he's just eliminating.
I'm talking about the other case, like
Okay.
where the
So now we know that there is some rectangle with 3 points of one color. If we are assuming, for the sake of contradiction, that this does not happen. That is what he did. He just did the case when everything is like this. Does that make sense now?
in the first case it does make sense, but not in the second.
So in the second case, all we know is that there is some triangle that, like we're not done with the case, we're still doing that case. We just know that there is some triangle which has three vertices of the same color. Like, I don't think that is necessary because I think we can show that such a triangle exists anyway. It's just that he eliminated the case where every triangle has like two red and two.
You mean a rectangle, right?
Yeah, every rectangle.
Okay, I guess in this too, if we extend it, then
Yes.
we'll be out of the cases once and we'll get two
Mhm.
similar patterns.
Yeah. So basically, I think you can just take a line. Yeah, take a line which has say 3 points of some color. And so if you take these 2 points, you know that over here you can't have two red points. So if you have a red point, you need to have a blue point over here. Like if you're assuming for the sake of contradiction that this kind of rectangle does not exist. And at some point, if you ever have two blue vertices like this, then after that, however down you go, if you have a red point, then like perpendicular across from that, you need to have a point, a blue point. So like any pair you take will be of opposite colors. So that means that like for infinitely many pairs as you go down, they will have opposite colors. But the thing is, you can do that over here as well. So if say this is red, this one has to be blue. So then these two will match. And that means that you can't have any two blue points on this line and this line. That means you need to have a red here, which means you need to have a blue over here, which means you need to have a red over here. So basically, at some point, it kind of just works out.
In the third line, if we draw the second point, then it must be red.
This point,
Okay. Okay, could be blue too. Okay.
yeah. But then that means that the third point must be red. So, yeah. Okay, so I hope that's
So
fine.
So
Yeah.
if you write like a formal solution to this, like do we like write two cases? Like
Actually, we don't really need two cases. We can just say some line must have, say, an infinitely many number of red points. So just either red or blue. So assume it's red and just take 3 red points on that line and then do this argument. Like you actually don't need to eliminate this case.
okay. And also we didn't need PHP. Like it's just a comedy problem here.
This is not exactly PHP. I think you can kind of think of it as thinking of the combinations of red, blue, red you can have on this line. And you know that some two combinations eventually end up being the same. But then that means that you have, say, like 2 reds and then 2 blues. So 2 reds and 2 blues cannot ever appear after that. And then you can use this argument of like alternating reds and blues, if that makes sense. It's not exactly PHP, just similar kind of feeling. Okay. So if everyone was clear with that, we'll move on to infinite PHP. So infinite PHP is very simple. It just says that if you have infinitely many things and finitely many holes, some hole must have infinitely many things. And that's because if not, you have just finitely many things in all the holes. So that's like very easy to prove. And we'll try some problems based on that. So this is the first problem. So you can try it. And the statement might be a little confusing, so if you have any doubts, please ask.
So the initial like the directions of the grids don't matter. Like the insect just moves as it likes until it reaches a wall.
Like, yeah, the initial, yeah, it could be any configuration. It just moves in the directions given. So what could be your finitely many holes here? Like you have 100 by 100 squares, right? So that's a finite number of positions the insect can be. And if you're assuming it stays in the board forever, then that's like infinitely many positions it can have in the boards. So what can you say about it?
So that means the insect like stays at one position for an infinite amount of time.
Yes, exactly. So there is some square where it stays infinitely many times. So what can you say about the squares around it?
Uh, isn't this impossible because there is a 90-degree rotation every time?
Yeah, the arrows rotate 90 degrees each time. But what we're looking at is if the insect, so like the reason for that is for the insect to not get stuck. Like, so for example, like if there is a wall and the insect goes here, the arrow is over here, then he gets stuck, right? That's why the arrow rotates and then it becomes like this, so he can move. So he can always move, but the question is whether he can get to the opening and get out or not. So what we're doing is we're assuming he can't. That means that he stays in the board forever. So like he is in the squares infinitely many times. So he must be in some square infinitely many times for sure. Does that make sense?
So if the insect is in like a corner position, then even if the arrow like moves clockwise, it'll be against a wall. So in that case,
Then the
it's
arrow
gonna be-
moves again.
or it keeps
Like
moving all the time.
like if the movement can't be done, then the arrow moves 90 degrees clockwise. And if the movement still can't be done, the arrow moves again.
Oh, okay. So
And the only time the arrows change is when the insect cannot move. So now just think about different cases. Like suppose the infinite square is surrounded by other squares. So what can you say about the number of times the insect goes into these squares?
One of them has to be infinite.
One of them has to be infinite for sure, but uh, is it only one of them? Like, okay, when the insect leaves, so suppose the arrow is this way, then the insect goes over here, then the arrow changes. Like, then it becomes this way. So the next time the insect comes to the square, it must go into this one. And the next time this one, and then this one. So actually, it goes into all of them infinitely many times. And then you can just repeat the argument. And you'll have to modify it a bit for the edge squares and corner squares. But essentially, you'll get that it goes into each square infinitely many times. Like if it's on an edge and say it moves this way, next time it moves this way, next time this way. And then after that, the arrow will be this way. But it can't go there. So the arrow will change again to this direction. And similar argument for corner squares as well. So basically, if an insect is in one square infinitely many times, it will be in the adjacent squares also infinitely many times. I hope everyone sees why that is. If not, please say.
Can I
So-
ask a question?
Yeah.
Yes, so we're like assuming like there are like an infinite amount of number of pigeonholes, because we're assuming like the insect never leaves the grid.
No, so there are an infinite number of pigeons. Like we are taking holes as the squares of the grid, and pigeons
so-
as
yeah.
the insect
But
being in the
that's
square.
That's only when like the insect never leaves the board. Only then we can
Yeah,
assume
yeah.
like infinite. Yeah.
Yes. Okay, so we are almost done. Like we can then show that like the square next to the opening, the insect enters here infinitely many times. And that means that in one of the times the arrow must be going this way. So it can be.
Can you
So I
please
hope that,
comment
yeah.
that it goes to the edges infinitely many times? I couldn't really follow up.
Okay, so we showed that if it enters some square infinitely many times, it enters all the neighboring squares infinitely many times. Is that part fine?
No, I couldn't get that part now.
Okay, fine. So suppose it enters, say, the square infinitely many times. Okay, so the first time, if the arrow is pointing this way, the insect's gonna go out this way. And suppose it somehow comes back. So when it comes back, the arrow will still be pointing this way because it won't change, right, according to the rules. So the arrow just changes after the insect moves. So if the insect has moved this way, then the arrow just changes like this and it remains that way until the insect comes back. So when it comes back, it's going to go this way to the right. And when it moves, that time the arrow will change and will be pointing down. Because the arrow changes only either when the insect moves or when it can't move, like if it's stuck. Right. So the
Okay,
third time, okay, did you get it now?
yeah, but how can we show that it moves into a square infinitely many times?
That is the pigeonhole principle. Like we know it stays on the board forever. So it must, and each time it changes the square it's on, right? So it must enter some square infinitely many times. And if it enters this one infinitely many times, from here it goes into each of the directions alternatingly. So it must enter all of these also infinitely many times.
Okay, got it.
And you just extend the argument and then you get that everywhere it enters infinitely many times.
But eventually leave the square.
Yeah. Okay. So now try this problem. It's a little bit different, but yeah, it uses the same kind of idea. Basically, you're given an infinite graph of two colors, and it's like a complete graph. And you want to show that there's an infinite clique of just one color.
maybe we can assume for the sake of contradiction that there is only a finite number of points with uh, like do we say it in the graph language?
Yeah, you can assume that such a clique does not exist. I think in this case, whether you assume that or not doesn't really matter. You just sort of try to start finding a clique, and then you can do something to force it to exist. Like, what kind of points could you have that would ensure that such a clique exists? Try to think about that a little.
Like if we start with a red point and like assume like it has no assume it has no blue neighbors in the beginning, neighbors meaning like no blue segments are connected to it, then like if we go to a blue segment point and then we assume like no red segments are connected to it, but it's a contradiction because like the initial point was red, and so like we can like go on forever.
Yeah, the idea is going on forever, but you need to show that you can. So, like, if you start from a point, you know that it must have at least like either infinitely many red neighbors or infinitely many blue neighbors. That's how you're using the infinite PHP. So, if it does say have infinitely many red neighbors, and suppose like this is the set of like the infinite set of neighbors, you pick another point here if it also has infinitely many red neighbors. And if you can keep on finding points here which satisfy this, which go on forever, then you are kind of done. Like you have an infinite number of points and all the segments joining them are red. So what happens when a problem arises? Like problem happens when you keep doing this and you end up with some point and you like some point and it does not have any neighbors with infinitely many red edges. Because if it did, then you could keep going. So this is when the problem comes. Like all of these points have only finitely many red edges. So then what can you do? Because I hope this is clear to everyone. Like basically you want an infinite sequence of points such that each of them has infinitely many edges of a particular color. And each of them is connected to the next one by that color itself. Because that just becomes your infinite peak.
This means that every that there exists a leaf, no, something like that.
Um, Not exactly. Like basically what you know about these points is that they form an infinite set and all of the points in that set have finitely many red edges, which means they have infinitely many blue edges. So now maybe try to do the same thing we did with red, try to do it with blue in this set and see why you can't get a contradiction. Like see why the same thing cannot happen again. Like this is a new set, call it S. And you know that every element in S has infinitely many blue edges and finitely many red edges. So try to do the same kind of thing again. And so again, I'm saying that what you want is you basically want a set of points such that each one is connected to all the next ones by that same color. So you're basically taking an infinite set inside an infinite set and so on again and again.
I was curious how at the first point did we assume that a point is connected to infinitely many points? many points with red segments, because that just finishes the problem. No.
No, it doesn't. Like, we know that every point is connected to every point that is given. So if you take a particular point, either red or blue, with some color, it must have infinitely many edges. So we're just taking that color. We are assuming it's red, like without loss of generality. Like basically, you want some infinitely many points such that each of their edges with each of the others is just one color. That's what you're looking for. So if you take this one, if you take all of the neighbors over here, you don't know that all of the mutual edges are red. That's why you cannot just finish it then.
Okay, so this is that every point is joined to every point with the same
Yeah,
edge.
you want to plead. Okay, so try doing the same thing again. So now you have a new set. You have obviously infinitely many points in it. And you know that each point in this has finitely many right edges. So again, you take a point here. You know it has infinitely many blue edges. You take one of the neighbors. And again, you know it has infinitely many blue edges. So you take one of those neighbors and you know that this is connected to everything here by a blue edge because everything you're doing is in the set of neighbors of the initial point, right? And so again, you keep going in this way. And now if you have a contradiction, if say at some point you get some point which has really finitely many blue edges, then that's a contradiction because it can't have both finitely many red edges and finitely many blue edges. Because this is within a set where you already know that each point has finitely many red edges. So that's why you're getting a contradiction.
Okay, since every point was connected by some red or blue.
Yeah, like every point needs to be having infinitely many red edges or infinitely many blue edges by definition. So I know that this might have been a little bit confusing to follow, so I'll just explain the whole thing again. So you start with a point, assume it without loss of generality, it has infinitely many red edges. So you take all of those neighbors. So you have the set of neighbors at this point, and everything here is connected by a red edge to this one. And now you take a neighbor. If it also has infinitely many red edges, you do the same thing again. And you already know that this is connected with a red edge to everything in here. Then you just keep repeating that argument. If you ever get stuck, that means you have this set of points and all of them have infinitely many blue edges. So now you start here again. You take a point, take some neighbor connected by a blue edge, and like you basically take the set of neighbors connected by a blue edge, take one of them, and take its set of neighbors, and you keep going. And again, here you know that everything here is connected by a blue edge to each point that comes after it. So now the only issue is what if again you have a set in which nothing has infinitely many blue neighbors, but then you have a contradiction because you know that all the points you have finitely many red neighbors. And that means that some point has both finitely many red neighbors and finitely many blue neighbors, and that's a contradiction. So since each point has infinitely many blue neighbors in the set, you can always keep going.
What if it was like red, blue, red, blue?
No, because you can't get stuck a second time. Because in this set, the second time you do this, the extra information you have is all the points have finitely many red neighbors. So you can keep doing it with blue in this case.
Okay, got it.
Okay. So if anyone else has any questions, please ask. So if not, I'll move on to the next problem. This is not really infinite PHP, it's just normal PHP problem. So you're given an equilateral triangle with side length 1 and some 5 points are marked in it, and you have to show that some 2 of them are at a distance of half of, like, at most half from each other.
If we divide that triangle into 4 equilateral triangles.
Yes, that is the idea. So you just take the midline, take all 3 midlines, and you get 4 equilateral triangles, which are of area 1/4. Then what do you do by PHP? Like by PHP, some 2 of the 5 points must be in the same triangle. And like any distance in this triangle can be at most half because all the sides are half. Yeah, so the main motivation here is you want to show something about distance less than half. And you have 5 points, so maybe you want a PHP with like 4 points. So that sort of motivates constructing the midlines and dividing it into 4 triangles. Okay. We'll do one more problem and then we'll wind up. So you're given n integers and you want to show that there exists a subset of them whose sum is divisible by n. Like the subset obviously has to be non-empty, otherwise it's stupid.
So the subset, for the sake of contradiction, the subsets could have 0 to n minus 1.
Yeah,
Subsets could have 0 to n minus 1 sum mod n.
1 to n minus 1 model.
Okay, yeah, 1. And since there are n integers, so
Yeah.
uh, like we could name the sums like s1, s2, sn like this.
Okay. Like
There will
all
be
the possible sums.
so any two of the sums would have equal will leave equal remainder when divided by n, like equal mod
Yeah.
n. So
Okay.
just subtract subsets, the
Oh,
bigger
so
subset.
are you? Yeah, but you need to know that one of them is contained within the other. You need to define sums in that way.
We
So
could one, then one, two, then one, two, three.
yeah, exactly. So if you have A1, A2 till AN, what you want is you want to do some PHP thing and get that some two subsets have the same sum. And you want to be able to subtract one of them from the other. So because of that, that motivates you to define subsets which contain one another. So if you define the first sum as just A1 and then A1 plus A2 and so on, and Sn just becomes all of the sum. Then you have n sums here, but you only have n minus 1 possible residues mod n. So sum 2 will have the same residue modulo n. You can just subtract the smaller one from the bigger one, and then you'll get some terms which are divisible by n. Right. So I hope that makes sense to everyone. And I hope the motivation also is clear.
Was there any more general version of this? Because I read this problem like a week ago or so. Was there any a general version?
I don't think this, like, I don't see how it can be generalized more. And think about it. But yeah, there's no general notion that it works right now.
Okay.
Okay, so yeah, if any of you have any questions about any of the problems, you can let me know now. Otherwise, we'll end the class.
Like, can I ask a question like in general PHP?
Yeah.
So basically, like we're always looking for like n+1 pigeons and n pigeonholes. Like, will there be any cases where like it could be like n+I pigeons and
Yeah,
pigeonholes?
yeah.
Like,
Yeah, like anything is possible. There's also the general form, which is like a ceiling of n by k. Just that sometimes if you know that something is going to use PHP, you look for something of that form. Like for example, over here we knew that you have 5 pigeons. So you want to look for like less than 5 holes somehow. That was just because it's a small number. But in general, when you have a lot of things and some number of categories, and different things are in different categories, that's when you might want to like try using Pigeonhole and see if it gives you any information.
okay.
Okay. Any other questions? Okay, if there are no questions, I'll end the class now. Thank you for attending.
Thank you.
Thank you.